Chlorine dioxide, or ClO2, is a fast-acting, highly effective biocide. It has been studied for 200 years and used commercially for over 70 years. International Dioxide Incorporated is a leading provider of ClO2 technologies and chemistries for over 65 years. Applications for chlorine dioxide include municipal water treatment, wastewater treatment, bacterial control in cooling towers, and food and vegetable processing. International dioxide ClO2 offerings have recently gained wide acceptance in the oil and gas industry as an effective biocide. It is approved by the U.S. Environmental Protection Agency and the World Health Organization for use in drinking water and can be used in most large applications where chlorine or bleach is currently in use. Chlorine dioxide functions as a highly selective oxidizer with less environmental impact than other biocides. ClO2 readily oxidizes electron-rich chemicals such as sulfide, iron, manganese, and organic molecules with electron-rich groups. In this reaction, sulfide ion is reacting with ClO2 to form elemental sulfur, or in some instances, sulfate. Most notably, ClO2 oxidizes troublesome phenols to quinones. However, many organic molecules are less electron-rich and not easily oxidized by ClO2. Consequently, chlorine dioxide minimizes wasteful reactions with organic molecules, in contrast to more aggressive, less selective oxidizers. This conserves ClO2 for its intended disinfection purpose. The strength of a given chemical to act as an oxidizer is represented by the standard reduction potential, SRP, which is measured in volts. As shown in this table, chlorine dioxide has an SRP of 0.95 volts, which makes it a less aggressive oxidizer compared to many other common disinfectants used in water treatment applications, such as ozone at 2.07 volts and hypochlorous acid at 1.49 volts. In addition to its oxidative selectivity, chlorine dioxide has 3 more distinct advantages over chlorine as an oxidizing biocide. First, because ClO2 does not undergo hydrolysis in water but remains a dissolved gas, it is able to maintain its oxidative properties over a broad pH range, from very acidic environments below pH 4 to basic environments of pH 10. Chlorine, on the other hand, has a narrow pH efficacy range and is a relatively ineffective antimicrobial in alkaline environments. Second, ClO2 is a 5-electron oxidizer and on a per-weight basis provides 2.6 times the oxidative capacity of chlorine. Third, ClO2 does not chlorinate organic molecules as does chlorine. Chlorine can react by addition or substitution reactions, which incorporates a chlorine atom into an organic compound. This leads to the formation of harmful chlorinated disinfection byproducts, such as trihalomethanes, THMs, chloroform, and dioxins. Compared to other oxidizing biocides, all these attributes make chlorine dioxide a very effective and efficient choice for disinfection. Disinfection contact time is generally shorter. The treatable pH range is wider, the resulting dosage is lower, and harmful byproduct formation is minimized. And as demonstrated in the EPA's Office of Drinking Water Guidance Manual, ClO2 is a very strong disinfectant with a CT value second only to ozone. The CT value is defined as concentration multiplied by time to achieve a desired disinfection performance. The lower the number, the stronger the disinfectant. Chlorine dioxide doesn't form chlorinated organics like THMs or HAAs. The decomposition byproducts of ClO2 generated by sodium chlorite include chlorite, chloride, and chlorate ions. Depending on the water makeup, approximately 40 to 70% of the applied ClO2 dosage will revert to chlorite ions. 20 to 40% of the applied dosage will convert to chloride, and less than 10% of the applied ClO2 will convert to chlorate ions. chlorine dioxide, chlorate, and chlorite will all eventually decompose into chloride ions and typically become reassociated with earth mineral cations to form simple salts such as sodium chloride, table salt. Chlorine dioxide, when generated by sodium chlorite, is one of 4 U.S. EPA disinfectants approved for potable water use. When applied at the appropriate concentrations, chlorine dioxide does not form any appreciable halogenated byproducts, and the ClO2 residual byproducts are typically within the recommended EPA limits. Chlorine dioxide kills bacteria through multiple mechanisms. In bacteria, chlorine dioxide oxidizes fatty acids and membrane lipids in the cell membrane. This disrupts the permeability of the outer membrane, resulting in the inability of the cell to regulate the movement of molecules into and out of the cell. ClO2 also denatures cellular proteins in the membrane and within the cell itself by oxidizing amino acids that make up these proteins. As a result, the proteins change shape and lose functionality. This can make the cell unable to generate energy, unable to move molecules in and out of the cell, and unable to stay alive. In bacterial endospores, the inner membrane is essential for viability. ClO2 penetrates and damages the inner membrane, making the spore leaky. In viruses, as shown in this RNA virus, ClO2 reacts with the protein capsid, allowing RNA to be released. The RNA then reacts with the ClO2, and RNA synthesis is disabled, so the virus cannot replicate. These reactions with cellular biomolecules result in impairment or death of the microorganism. The collective damage from this multifaceted attack prevents the microorganism from developing resistance and makes ClO2 both broad-spectrum and efficacious at a low dose. Chlorine dioxide destabilizes biofilm formations and provides ongoing control of biofilm regrowth. Biofilms are known to reduce flow, increase pressure, and provide shelter for sulfate-reducing bacteria, SRBs, and acid-producing bacteria, APBs. These bacteria are known to cause significant corrosion in piping and fluid handling systems. As a true dissolved gas in solution, ClO2 rapidly penetrates into the biofilm substrate, delivering biocidal effectiveness throughout and beneath the biofilm, essentially eliminating underlying APBs and SRBs where they live. In addition, as chlorine dioxide reacts as a biocide, chloride ion is formed as a ClO2 disinfection byproduct. When chloride ion encounters acids, such as those produced by SRBs and APBs, chlorine dioxide is reformed in situ. In effect, a cycle of chlorine dioxide consumption to chloride ion and a partial regeneration back to chlorine dioxide is possible in many biocidal applications, including biofilm control. ClO2 is a well-recognized biocide treatment for cooling water and process water applications, especially when biofilm removal and inhibition is the goal. Chlorine dioxide is a fast-acting, highly effective oxidizing biocide. Microorganisms are known to alter their structure to develop immunity to non-oxidizing microbicides. The typical solution to this problem is to alternate non-oxidizing biocidal chemistries. When treating with ClO2, microorganisms typically found in industrial and municipal processes cannot alter their structure or develop immunity. ClO2 rapidly diffuses through cell membranes, oxidizing critical proteins and amino acids inside of the microorganism. These reactions disable cell metabolism and prevent microorganisms from developing a resistance mechanism. The use of chlorine dioxide eliminates the need to alternate biocidal chemistries in critical applications like food sanitation and drinking water disinfection. International Dioxide offers a comprehensive biocidal water treatment solution using chlorine dioxide chemistry that has been proven in applications from municipal drinking water to food processing for over 65 years. International dioxide ClO2 offerings have recently gained wide acceptance in the oil and gas industry as an effective biocide. With over 1,000 ClO2 generators installed at customer sites worldwide, International Dioxide combines application experience, analytical support, equipment design, and a focus on safety, along with a reliable chemical supply, to offer an exceptional chlorine dioxide experience to all of the industries we serve.